Ngalakin kadijan nyunga boja.
Good evening, everyone. In the last lecture, we spoke about how to draw positive sequence circuit, zero sequence circuit, and negative sequence circuits. So we've looked at that, and we made a start on fault calculations, asymmetrical fault calculations. And in doing asymmetrical fault calculations, our first step is to actually draw the Thevenin equivalent circuit at the point where the fault occurs. So at the point where the fault occurs, we draw the Thevenin equivalent circuit of the zero sequence, the positive sequence circuit, and the negative sequence circuit. So the Thevenin equivalent of all the three sequence circuits we need to draw. So before the fault occurs, we assume that the system is balanced, and we draw the zero sequence circuit, and the zero sequence circuit would look something like this. Notice that there is no voltage source. The reason being the reason being the circuit is balanced before the fault occurs. So our first step is to draw the positive sequence, zero sequence, positive sequence, and negative sequence circuits, the Thevenin equivalent at the point of fault. So the zero sequence circuit would look something like this, right? Would look something like this. And the positive sequence circuit will take this form where we some voltage source and some impedance. And how to draw these positive sequence circuits we discussed in the last lecture, so I'm not going to go over it. But when we take the Thevenin equivalent, the positive sequence circuit would look something like this. And the negative sequence circuit again would look identical to the positive sequence circuit without the voltage source again. It will look something like this. Again, the reason for not having a voltage source here is because the circuit is balanced before the fault. When the circuit is balanced, the negative sequence circuit and the zero sequence circuit will not have a voltage source in its circuit. Now, how to draw these sequence circuits? We've looked at it in the last lecture. I'm not going to talk about it. Yeah. For a moment, I actually thought I'm speaking to an empty class, but it's good that you guys turned up now. Right. Are you listening to it? All right. Okay. Okay, that's good. At least you guys are there and some online, joining online, so that's okay. But it's difficult to talk to an empty class, so it's good that you guys are there, right? All right. So when we do our fault analysis, right? Now we have the three circuits: the zero sequence, the positive sequence, and the negative sequence. Now, depending on the fault, we connect the circuits in a different way. Now, if it's a balanced fault, if it's all the three lines connecting to ground, right? All the three lines connecting to ground, then the circuit is still balanced. So it's a balanced fault. In this situation, what we do, we take the zero sequence circuit and we short circuit its terminals, right? We do the same thing with the positive sequence and the negative sequence circuit. We take its terminals and we short circuit. That's if it's a balanced fault. If all three lines connect to ground, that's what we do. It's a bolted fault, so it's a short circuit. There is no impedance connecting the terminals to ground. Yeah? So in this situation, you can clearly see positive zero sequence circuit doesn't have a voltage source. Negative sequence circuit does not have a voltage source because we are talking about a balanced circuit, right? So there is no zero sequence current, there is no negative sequence current. Because if it's a balanced circuit, we only have the positive sequence circuit, that's all. Yeah. So we can now calculate the current, right? We know that this current is zero. We know the negative sequence current is zero. We can compute the positive sequence current, right? Yeah. And once you know the sequence currents, the phase currents are determined, right? Because the phase current is equal to A times matrix A is a known matrix times the sequence currents. Yeah, sequence currents. So what is IP? IP is IA, IB, and IF, right? The sequence current, the phase currents. And A is a 3x3 matrix, which we know. And IF is the sequence currents, which is the positive sequence, negative sequence, and zero sequence. Yeah? So, so we can calculate phase A current, phase B current, phase C currents because we know the sequence currents. That's a balanced fault, what we are looking at. Now, if the, oops, I got these things mixed up here. It's actually zero sequence, positive sequence, and the negative sequence. It's just the order is different. Yeah, the message is the same. If you know your sequence currents, you can calculate your phase currents. Yeah, okay. So here in the balance case, the zero sequence current is zero, the negative sequence current is zero, the positive sequence current, we have computed it because it's quite easy to calculate this current, just the division of the voltage by the impedance, and that's what goes in here. And this is the known matrix A where alpha equals 1 angle 120, right? So matrix A is known, this is matrix A is known, we can calculate those currents, phase currents. So the reason that we've looked at all the sequence circuits is because we want to study the asymmetrical faults. Single line to ground fault is an asymmetrical fault. Yeah, because after the fault, the circuit is not balanced. Because we have one line connecting to ground, as you can see here, one line connects to ground. That is phase A touches the ground through some impedance ZF, B and C are open. Right? So what can we say? In this situation, the phase current A will be something. Phase current A will be something we don't know. Phase current B is 0. Phase current C is 0. Right? Because they are open. No current. So what are the zero sequence, positive sequence, and the negative sequence currents? Because if you know the phase currents, we can calculate the sequence currents because they are related through this A inverse. That's A inverse, right? Multiplied by the phase currents. And the question mark is the unknown current. The other two phase currents are 0. So what can we say here? So if I take this row and multiply by that, right? I'm going to get what? IF naught, right? Because of, sorry, IF naught equals 1/3 IFA, right? 1/3 IFA. If I look at the positive sequence current, again the answer is going to be the same. I take the second row and multiply by that vector, right? It's the same. IF negative is the same, right? So what we see from here is the three sequence currents are the same in this particular scenario. When there is one line connecting to ground, all the sequence currents are going to be the same. That we can see that. What can we say about the phase voltages? So phase voltages are related to sequence voltages in this way, right? So phase A voltage is the first row multiplied by that vector, which is the zero sequence voltage, positive sequence, and the negative sequence voltage, right? Which is equal to right? So if I'm looking at phase A, right? If I'm looking at phase A, it's equal to 3 ZF times IA, right? Because the voltage at phase A is the current that flows through here, which is currents that flows through ZF is phase current A times ZF, right? Times ZF, yeah? Now, IAF is equal to 3 times F0, so we have this formula. 3 ZF IF0, or we can say IF plus because they are the same, or IF minus is the same. So VAF, the phase current at A, is simply 3 times ZF, which is the impedance that's connecting phase A to ground, times the sequence current, positive sequence current, fault current. So these are two key equations. This equation and this equation are key equations that we have just derived. So how do we then utilize those two equations to connect the circuit? I said the type of fault determines how you connect the 3 sequence circuits. So here are the 3 sequence circuits. Here is the positive zero sequence circuit. This is the positive sequence circuit, and that's the negative sequence circuit, right? Now, how do we connect? Depends on the type of fault. All right, so what can we say? We know that in this particular case, the 3 sequence currents, we know that the 3 sequence currents have to be the same, right? The 3 sequence currents are the same, yeah? So, to make the 3 sequence currents the same, we need to connect the 3 circuits in series because the same current has to flow in all 3 circuits. So you can see we have connected the 3 circuits in series in this situation. Yeah, because that is clear. Otherwise, the 3, well, that's a possible way that we can make sure that all the 3 sequence currents are the same. Then on top of that, we have to make sure that the VAF is actually 3 times ZF times the sequence current, right? So here it is. So this part here has to be 3 times ZF, because if that is 3 times ZF, then we have VAF, which is the sum of, VAF is the sum of the 0 sequence voltage, positive sequence voltage, and the negative sequence voltage. So the voltage drop across the impedance 3 times ZF is V naught 0, V plus, and V negative, right? Has to be 3 times ZF times the sequence current that flows through that. Yeah? So in order to satisfy these 2 equations that we've just derived, the sequence currents are the same, and the sum of the sequence voltages is 3 times ZF times the sequence current, 0, positive or negative, the circuit has to be connected in this way. Right? Circuit has to be connected in this way. So all we have to remember is if there is a single line to ground fault, we find the Thevenin equivalent of the 0 sequence circuit, Thevenin equivalent for the positive sequence circuit, Thevenin equivalent for the negative sequence circuit. At the point where the fault occurs, we connect them in series, right? And we connect 3 times the impedance that connects the line to ground, and that's the circuit that we need to analyze, and the current that flows through that impedance is the fault current. Okay, so to do a little example, if we assume that the fault voltage is 1.05, in other words, where the fault occurs on the network, right? Where the fault occurs on the network, right? Before the fault, the voltage is 1.05 angle 0, 1.05 angle 0, and it's a bolted fault. Bolted fault means this part here is 0. ZF is 0. And the parameters are the same as in the last example. In other words, 0 sequence impedance is that, positive sequence impedance is that, negative sequence impedance is that. Then what is the fault current? Well, we can calculate the sequence currents to be the voltage VF divided by all the impedance values, right? And we know that the phase current and the sequence current are related through this equation, IP A times IS. So IAF is simply I0 plus IF minus. Why? Because this thing here is, this is IA, this is IB, this is IF, must equal, this is matrix A is 1, 1, 1, right? And here we have 0, positive and negative, right? So IA is just the sum of sequence currents, okay? So it's 3 times that, yeah, is the IAF. And of course, if you do calculate IBF and ICF, it will be 0 because there is no current flowing through. They are open terminals, right? There's no current flowing through that. So that's the single line to ground fault calculation. And here we are looking at a line to line fault, okay? Single line to ground is what we looked at. Here we are looking at line to line fault. Again, there is an impedance that connects the 2 lines, ZF, okay? So again, in analyzing this, then we are trying to determine those 3 sequence circuits, how are we going to connect them? Because if you know how to connect them, then we can determine the fault currents. Okay, so by observation, what can we say? By observation, we can say the phase current in line A is 0 because it's not connected to anything. And we can say the current that flows in B, which is in this direction, and current flows in C is in this direction. They are in opposite directions, flowing in opposite directions in the impedance. So we can say that, right? And we'll assume ZF is 0, but it doesn't have to be. In this situation, the voltage at point B relative to ground and voltage at point C relative to ground is the same because they are connected. So those we can write. So what can we say here now? All right. So here is on the left hand side we have the sequence currents. On the right hand side we have the phase currents. So it connects through A inverse, matrix A inverse. And we can say that IA is equal to 0, right? IBF and ICF is the negative value of that. Current that flows in phase C is the opposite of the current that flows in phase B, right? So that's that negative sign, okay? Now, if we now calculate the zero sequence current, this whole row multiplied by this whole column will give me 0, right? Now, does that also make sense? It makes sense because there can't be any zero sequence current here because there is no path to ground. There is no path to ground. Zero sequence current to flow, there has to be a path connecting to ground. There is no path connecting to ground here. So zero sequence current is 0, so that makes sense. So IF plus is the second row multiplied by the column, which gives us this expression. IF minus is the third row multiplied by this column. So we can easily see then positive sequence current is related to the negative sequence current through minus 1, multiplication of minus 1. Right? Right. So here we try to relate the zero sequence voltages to the phase voltages, again related through matrix A inverse. And we see that if we write this, so first VF plus, so second row multiplied by the column vector gives us this, and the third row multiplied by the column vector gives me that. We have used the fact that VCG and VBG are the same because it's a line-to-line fault, so they're short circuit, they're connected together, right? So from this we see that, so we've used this fact because it's a line-to-line fault. So from these two expressions we see that the positive sequence voltage and the negative sequence voltage are the same, right? Okay, so what does our analysis show? The positive sequence voltage and the negative sequence voltage are the same. Our analysis also shows that the positive sequence current is in the reverse direction of the negative sequence current. So that tells us the positive sequence circuit and the negative sequence circuit needs to be connected in parallel. Because if they are connected in parallel, this VF plus and VF minus is the same, right? And if they're connected this way, you can see the positive sequence current, which is flowing that way, and the negative sequence current are in opposite direction, but has the same magnitude, right? And the zero sequence circuit doesn't connect to anything because zero sequence current is 0. There is no zero sequence current. So if there is a double line fault, line-to-line fault, you take the sequence circuits and this is how you connect them, right? This is how you connect them. And see, when you connect them, you need to know where the positive sequence voltage, where the negative sequence voltage, etc. are. So you know that this is the positive sequence circuit. You know that this is the negative sequence circuit. You also know that the positive sequence voltage has to appear across these terminals, these two terminals, positive sequence voltage. Negative sequence voltage has to appear across those two terminals. And we have connected them in parallel because they both have to be the same. That's what our analysis shows. And you also need to know the direction of and where to find the positive sequence current, because obviously it's in the positive sequence circuit, and same with where to find the negative sequence current. And if you connect it this way, then the two currents are in the opposite direction, right? This is a zero sequence circuit where the voltage, zero sequence voltage appears across the terminals, and the zero sequence current is flowing into the terminals. But since the zero sequence current is zero, it cannot be connected anywhere. It's like that. So now you know how to analyze three-phase to ground fault, which is symmetrical fault. You know how to analyze a line to ground fault, because you connect the three circuits in series, right? And here now you know how to analyze a double line to line fault, because this is how you connect the circuit, the three circuits. All right, so this is a calculation. So the calculations are then very simple. If we assume fault voltage is 1.05, ZF is 0, in other words, bolted fault, and other parameters are same in the last example, so those are the sequence impedances, then we can calculate IF plus. So you know the impedance values here, you know the voltage source, you can calculate IF plus, right? It's a very simple circuit. IF plus would be the voltage divided by the positive sequence and the negative sequence impedance, right? So which is that, positive sequence and negative sequence impedance, that and that. Oh, we don't care about the zero sequence. So positive sequence and the negative sequence impedance, which is these two values. This VF value is there, VF value divided by that. So we have IF plus, right? So this is IF plus. IF 0 is 0, zero sequence current is 0, we know that. IF minus is the negative of IF plus. And then, yeah. And, okay, sorry, I'm pointing to the wrong one. So this is the zero sequence current is 0. This is the positive sequence current, which we just calculated. Negative sequence current is the negative of that. And if you multiply by matrix A, pre-multiply by A, and then you have the currents. And you can see line B and C were short circuit. Was a short circuit. Line A is not connected, so the current in phase A is 0. And you have currents in phase B and C, which are flowing in the opposite directions, right? Makes sense. Then we can solve for voltages as well. Positive sequence voltage is just the voltage that appears across here. We can calculate that because we know that, we know the current. Therefore, we can calculate VF plus and VF minus, which are the same, right? We can calculate VF plus, which is this value here. VF minus is the same. A zero sequence voltage is 0. So this is the positive sequence voltage. This is the negative sequence voltage. This is matrix A. If you multiply them, then you have the phase voltages, right? Phase A voltage, phase B voltage, and phase C voltage. So we have those phase voltages. Does that make sense? Yeah? All right. So now we have a double line to ground fault, right? That's the last one. So what do we have in this situation? We have the lines A, B, C, right? So we'll assume that the double line to ground fault is between A and B and connecting to ground through an impedance ZF. So what can we say? We can say IAF is 0 because nothing flows there, right? It's open. What else can we say? VBG and VCG has to be the same because they are now connected, right? And it must equal the current that flows in phase A, current that flows in phase B. They sum together and flows through ZF, which is that. sum together and they flows through ZF. So that's what we can say for this double line to ground fault. So we can then say, okay, we have these two equations I have rewritten here. IAF equals 0, phase B and phase C voltages are the same, must equal ZF times the sum of two phase currents. From those relationships of currents, we can get the following equations. So the phase currents on the left relates to the sequence currents on the right. So we can say this value here is 0, so 0 must equal the sum of the sequence currents, right? We can say that. We can say that. And we can also say that 0 sequence current is no longer 0 because we have a path to ground. So 0 sequence currents can flow because there is something connecting to ground. Yeah. So, all right, so we have these relationships here linking the sequence voltages to the phase voltages through matrix A inverse. So we can then say VBGF, which is VBGF. So if I write the inverse of that, here is the phase voltages on the left linking to the sequence voltages on the right through matrix A. This is matrix A, right? So I can say VBGF, which is this voltage, right, must equal, which is this one here, VBGF, must equal the 0 sequence voltage plus alpha square times the positive sequence voltage. Why the positive sequence voltage and the negative sequence voltage are the same? Why are they are the same? Because this term and this term are the same, right? So if those two terms are the same, you can see the positive, this row multiplied by that vector, or this row multiplied by that vector is the same. Yeah? If VBGF and VCGF are the same, then positive sequence voltage and negative sequence voltage is the same by looking at the last two rows of that matrix, right? Because it's the second row multiplied by the vector, third row multiplied by the vector is the same thing. So we have this relationship, VF plus must equal VF minus. Yeah? So where are we? So VBGF, right? VBGF, second row multiplied by that, because we know VF plus and VF minus are the same, we end up with this expression. 1 times VF0 plus alpha squared times VF plus alpha times VF minus, which is also VF plus. So we end up with this expression. And we know that alpha 1 plus alpha squared must equal 0, because alpha is 1 angle 120, alpha squared is 1 angle 240. Right? So we have the relationship alpha plus alpha squared equals -1. If you sub that in, then we have this expression VBGF must equal the 0 sequence voltage minus the positive sequence voltage. We have that expression. So what do we have? So this section there, I deleted that. There's some typo there. Right. So what do we have for double line to ground fault? Double line to ground fault, we have this equation, right? We have, yeah. Now we also have IB, okay, let's have a look. IBF and ICF. IBF and ICF. Okay. Okay, so we can write these expressions. How do we write those expressions? We have IA, IB, and IC. Must equal matrix A times the sequence voltage I0, I positive, and I negative, right? So the first line here, matrix A, the first line is 1, 1, 1. The matrix A, the second line is 1 alpha squared alpha. Second line is 1 alpha squared alpha. Third line is 1 alpha alpha squared. So we have IB must equal I0 plus alpha squared IF positive times alpha times IF negative. So that's second row multiplied by this column, right? Is this equation here. Third row multiplied by this column is this equation here. So we got those two equations. If you sum IBF and ICF, if you sum the two, then you have 2 times, so you're summing IBF, you're summing these two equations together. So on the right hand side, you're going to get 2 times IF0, and you're going to get alpha times alpha plus alpha squared times IF plus alpha squared is -1. So you're going to get minus IF plus, and if I sum these two, I'm going to get alpha plus alpha squared times IF minus. Alpha plus alpha squared is actually -1, so you have minus IF0, right? So we have this expression, and we also have this expression because IA is 0, so that implies I0 plus IF plus I minus is equal to 0. That's the first row multiplied by the vector gives me this equation. So minus IF plus minus IF minus is in fact IF0. So then this whole term is just 3 times IF0. Okay? So we have these expressions. So this term here is 3 times IF0, which is this expression here. So VBGF, which is equal to VF0 minus VF plus, is 3 ZF IF0. We also have the sum of all the sequence currents equal to 0, and we also have this expression VF plus must equal VF minus, and that comes from here, which we discussed previously. Okay, so these 3 equations, although it looks I don't know whether it sounds a bit complicated, but it's actually not. Those are the 3 equations, right? I mean, you can easily derive them if you follow what I say. You can listen to it again if you haven't. In order to satisfy those 3 equations, you need to connect the 3 sequence circuits. So let me draw the 3 sequence circuits. The positive sequence circuit, this is the positive sequence circuit. This is the negative sequence circuit, this part here, right? And this is the zero sequence circuit, right? You need to connect those 3 circuits, right? The positive sequence circuit, the negative sequence circuit, and the zero sequence circuit. So let me do a different color for this. This is the zero sequence circuit. Let me do a different color for this. This is the negative sequence circuit. This is the zero sequence circuit, right? So I got different colors for the different circuits. So you need to connect the circuits in this way. Let's see if you connect the circuits in this way. Let's see if you can satisfy these 3 equations. Clearly, right? That the green line is a negative sequence circuit, so the current that flows in here is I negative. That's I negative. That's yellow is the positive sequence circuit, so the current that flows here is I positive. That's the negative sequence, zero sequence circuit, so the current that flows here is I zero. So you can see the sum of the currents, sequence currents, is actually zero because all three currents are flowing into a particular node. It's zero. Now, Vf plus must equal Vf minus, so Vf plus is across there, Vf plus. Vf minus is across there because the green is the negative sequence circuit. They are connected in parallel, so they are the same. So we can satisfy that. So the last thing that we need to satisfy is the first equation, is Vf0, which is this voltage, minus Vf plus, which is this voltage, right? So this voltage minus this voltage, right? Vf0 minus Vf plus must equal 3 times Zf times I0. So 3 times Zf times I0 flows through that. Right? So you can see those three equations can be satisfied provided we connect the sequence circuits in this way. Right? The derivation of those three circuits I've explained to you. Right? So the key points are this. Okay, we can do a little example, right? I'm not going to bother. Like, its example is you're given this value, you're given this value, this value, this value, and this value, and you calculate these currents because IF plus flows there, IF naught flows there, IF minus flows there, right? Vf plus appears there, and this Vf minus appears there, and Vf0 appears there, right? So you can calculate all the sequence voltages and all the sequence currents, and once you calculate all the sequence voltages, you can find the phase currents. All the sequence voltages, when you have calculated them, you can calculate the phase voltages, right? That's what that example is doing. So here is a summary. Asymmetrical fault, single line to ground fault. You draw the sequence circuit. This is the zero sequence, that's the positive sequence, that's the negative sequence, and you connect them in series through that 3 times ZF, which is the impedance connecting to ground, and you precisely know where to find the zero sequence voltage, positive sequence voltage, negative sequence voltage, and also the sequence currents. Then you can determine the phase voltages and phase currents after that, once you determine the sequence currents and voltages. Yes, you have a question? No, these are already in the form, the circuit connections are in the formula sheet.
The circuits form the different faults?
Yeah, I think so. Is it there? Is there anything for the faults? None of these circuits? Can you double check? Because that's important. If it's not there, you will have to know it, but I thought it is there. Can you check, please? Yeah. Sorry? Okay. So phase sequence, okay, equations, have a look, okay, let's have a look. You have equation 14, right? Connecting the sequence voltages and phase voltages. No, that's not given, right? So you would have to remember how to connect them. you will have to remember that single line to ground fault, that's the circuit, yeah. For double line fault, that's the circuit, right? It's not hard to remember, right? And double line to ground fault, that's the circuit. You will have to remember that, right? So let me explain, let me summarize, right? Let me summarize. So zero sequence circuit looks all the time like this, right? It's always like that. Z0, always like that. Positive sequence circuit always look like this. Always like that, right? For all types of faults, it looks like that. Negative sequence circuit looks like this. Always looks like that, right? Doesn't matter what type of fault it is, it's going to look like that. So if it's a single line to ground fault, then you connect them in series like that. This is the ZF, is this impedance. Yeah? Okay? And you have to know that the positive sequence voltage is here. Yeah? You have to know the zero sequence voltage is here. Yeah? You have to know that the negative sequence voltage is here. You have to know that. You have to know the positive sequence current flows here. You have to know negative sequence current, zero sequence current flows there. You have to know negative sequence current flows there. You got to know that, right? Okay, so it's not as hard as you think to remember it, and in some way it's good to remember it, because otherwise you don't know what you're doing, sort of. Yeah. So then line to line faults, right? You take the same positive sequence circuit, which positive sequence circuit is always like that, right? And that's the positive sequence voltage. You need to know that positive sequence current is like that. Yeah. You take that, this is this impedance there connecting the two things, and then you connect the negative sequence impedance, negative sequence circuit in parallel. So that is V minus, that is I minus flowing into the terminal, right? And this zero sequence circuit doesn't get connected, right? And double line to ground fault, well, that's the negative sequence circuit, that's the positive sequence circuit, that's the zero sequence circuit. And this thing here is that there, right? You got to know that. Then you can do the fault calculations. Yeah. So it's just you have to remember 3 circuits to be able to do that. Unfortunately, it's not in the formula sheet. At least you know you need to know that. And there are questions on fault calculations in the exam, right? So you can't afford to come to the exam without knowing how to do fault calculations. I'm telling you, there are questions. Yeah. So, so what we do is essentially just to in summary, that's how you, depending on the type of fault, you connect those in that way. But first step is, in the last lecture, remember, like you need to know how to draw this positive zero sequence and negative sequence circuit. And then let's say you have a fault occurring at some terminal, bus bar 2, like that, right? You need to find the Thevenin equivalent circuits for each of those sequence circuits, 0, positive and negative, at the bus bar where the fault occurs. That's the first step, which we talked about in the last lecture. I'm not going to go over that, yeah? So you need to know how to draw the sequence circuits. Then once you draw the sequence circuits at the bus bar where the fault occurs, you need to find the Thevenin equivalent circuit, right? When you find the Thevenin equivalent circuit, only the positive sequence circuit will have a voltage source. The zero sequence and negative sequence are not going to have voltage sources, right? It's not going to have, because the circuit is balanced before the fault occurs. Okay, so you need to know how to draw the sequence circuits. Once you draw the sequence circuits, you find the Thevenin equivalent circuit for each of those circuits, and then you connect them in a certain way depending on the type of fault. And in that circuit, you need to be able to identify where to find the positive sequence, zero sequence, and negative sequence voltage, where to find the positive sequence, negative sequence, and zero sequence currents in that. And then once you know those sequence voltages and sequence currents, you can find the phase voltages and phase currents through that relationship, right? Vp equals A times Vs, Ip equals A times Is. That's it. That's it for the fault calculations. Okay, so I'm going to talk about power system protection, right? Protecting power components in a power system. Power system protection components and purposes. Main idea is to remove faults as quickly as possible while leaving as much of the system intact as possible. So if there is a fault, we want to remove the fault, but we want to keep most of the network operating. Makes sense. So fault sequence of events, fault occurs somewhere in the system and changes the system voltages and currents because of the fault. Instrument transformers. So there are instrument transformers, current transformers and potential transformers, which are sensors, detect changes in currents and voltages. So do you kind of understand how a transformer can be used as a sensor? How can a transformer be a sensor? How can you use a transformer as a sensor? Say you're measuring a high current, right? With a transformer, you can actually drop the current into a smaller value, right? So if, let's say 100 amps are flowing, you drop to a 1 milliamp, for example, using a transformer. So that 1 milliamp will then indicate to me, because I know the turns ratio, that it's 100 amps flowing there. Same with voltage. So that's why if you're wondering, hang on, what current transformer sensor, the current transformers, so it's called CTs and VTs. CT, current transformer, VT, voltage transformer, can be sensors, right? So that's what it's written here, or potential transformers, PTs, same, voltage transformer. So so they are called instrument transformers, instrument transformers. So instrument transformers, either current transformers and potential transformers, sensors they can detect changes in currents and voltages. Because if there is a fault, there will be a huge amount of current flowing, and the voltages can drop, right? Because if it's short-circuited, voltage will drop. So overcurrent relays use sensor input to determine whether fault has occurred. So if the current transformer indicates a huge amount of current flowing through it, we know there is a fault. If fault occurs, relays open circuit breakers to isolate that fault. So you can open the circuit, because if you have a line, you can have circuit breakers on either side and you can isolate the fault by opening the circuit breakers. So 3 common components are used in power system protection. We need instrument transformers so you can detect a fault, right? Relays are needed so that you can activate the relays and circuit breakers to open the isolate a line. Yeah. So let's see how it works here. Power system protection components. Figure below shows a simple overcurrent protection system. This is an overcurrent protection system. So we have a line. So there is you can see there is a current transformer which picks up part of that current, right? So there's a current flowing in the main line. Current transformer just samples it. It's like sampling, yeah. So I dash is a pickup current. It activates a relay. It activates a relay, energizes a relay. When current flows through a coil, it will energize, yeah. And then it can close a contact, because when a coil is energized, it can close a contact because it can create a force, yeah. So obviously we can manually close a switch as well. We can close a switch because electrically, right, by creating a force when the current flows through a coil. So when that relay closes, this is a little battery, it energizes that coil, which we can open this breaker. We can open this circuit breaker. We can open this, yeah. So you can see there is a current transfer, is a bit of pickup current, energizes some relays, and then activates a circuit breaker to open it. That's what that is saying, right? So what are the types of power systems? There are two types of power systems. One is a radial network, and the other one can be a mesh network, right? So in the metropolitan, in the areas that close to the city where we live in, it's a mesh network. But if you are talking about in the country, it may be a radial network, because you can have a center point and then a one line extending, connecting one farmer, then another farmer and another farmer, and then another line going in a different direction, right? Radially going in a different direction, connecting another 2 or 3 farmers, like that. They're not a mesh network. So it can be a radial network that looks something like that, or it can be mesh network, right? Something like that. Radial or mesh. So protection is generally easier for radial network, but difficult for mesh networks. Right? So radial systems are primarily used in low voltage distribution systems. You know, you have the power network, you know, you have the transmission system, and then you have the distribution system, right? So radial networks are primarily in the distribution. Radial systems are primarily used in the lower voltage distribution systems. Protection actions usually result in loss of customer load, but outages are usually quite local. Right? We'll talk about that more. Many radial systems are protected by time delay inverse current relays, time delay relays. Adjustable time delays can be selected such that the circuit breaker closer to the fault opens, while the upstream breakers with larger time delays remain closed. Let me explain this. That is, the relays can be coordinated to operate in sequence so as to interrupt minimum load. So we want to coordinate the operation of circuit breakers. So let's say this is the source, right? So some transformer. This is circuit breakers here. There is a breaker here, and a breaker here. 3 circuit breakers, right? Say that we have a fault here. The fault is there at P2, right? So if a fault is at P2, we want to then disconnect, because okay. So consider fault P1 to the right of circuit breaker. Okay, no. We are talking about P1. Okay, yeah. So say that we have a fault say our fault is at P1, right? So if the fault is at P1, we only want to operate the circuit breaker B3. It's preferable, right? Because then we will only lose load 3. We still have load 2 and load 1 operating, supplying power to load 1 and load 2. So circuit breaker closer to the fault must operate quickly, and circuit breakers upstream, so B1 and B2 are upstream, right? Must operate after time delay if it's going to operate. So circuit breakers B2 and B1 will be like backup breakers. So if B3 must activate instantaneously, B1 after time delay, B2 after time delay, B1 even after a further time delay. But those will only, with time delays will activate if B3 does not disconnect because of a fault of its own.
So does that mean if there's a fault at breaker 1, then the entire network?
Yeah, if breaker 1 opens, the entire system is down. Load L1, L2, L3 all lose power. So in this situation, we only want L3 to lose power, but L1 and L2 to continue. So B3, so we can make sure that happens if B3, if B2 has a time delay, some time delay, and B3 has even a larger time delay, right? So consider a fault P1 to the right of circuit B3, which is at P1. For the radial system of figure below, for this fault we want B3 to open while B2 and B1 remains closed. Under these conditions, only load L3 is interrupted. We could select a larger time delay for the relay at B2 so that B3 operates first. It's exactly what I said. So thus far, any fault to the right of B3 provides primary protection. Only if B3 fails to open, B2 will open after a time delay, thus providing backup protection. Right? That's the idea. Yeah. So that way, the operation of the circuit breakers are coordinated. Because once B3 is activated and the fault is cleared, then the B1 and B2 won't be activated because currents are back to normal within that time period. All right, so here's a little example. Inverse overcurrent relay. Figure shows CO8 time delay overcurrent relay characteristics. So ECO8 is some type, right? So on the horizontal, you have multiples of the pickup current. The current transformer, there is a pickup current, right? So on the horizontal, we have multiples of the pickup current. Twice the pickup current, 3 times the pickup current, and so on. On the vertical axis, you have the relay operating time in seconds. So you can see for large, so think about one of these curves. What does it say? If the pickup current is small, the operating time can be bigger. If the pickup current is 5 times bigger, then the relay operating time is shorter. Yeah, makes sense because if the magnitude of pickup current is big, you want it to activate quicker, right? And then these particular curves, you can shift it up or down by choosing some setting. I can take this curve and shift it here if I go from 1 to 2. It's a dial setting that will shift those curves. Okay. So figure CO8 time delay overcurrent relay characteristics. The characteristic curve are usually shown with operating time in seconds which is vertical axis, a relay input current as a multiple of pickup current on the horizontal, as I said. The curves are asymptotic to the vertical axis and decreases with the current magnitude for values exceeding the pickup current. So for values exceeding the pickup current, the seconds activation time decreases. The inverse time characteristics can be shifted up or down by adjusting the time dial setting. So by adjusting the time dial setting, which is this, you can shift it up or down. Right, so here's the example. The CO8 relay, inverse time relay, with a current tap setting of 6 amperes. Right, so that's the pickup current setting. Pickup current setting is 6. Right, and a dial setting of 1 is used with 100 to 5 current transformer. Determine the operating time for pickup current of 5 amps. So if it actually measures 5 amps, but the magnitude for activation is set at 6 amperes. 6 amperes is a threshold, right? Is a threshold. So the ratio, is the multiple of the pickup current, in the sense multiple of the set pickup current. Set pickup current is 6 amps, right? Set pickup current, but the actual measured pickup current is 5 amps, right? So then the ratio is less than 1. As a multiple of pickup current, 5 amp as a multiple of the set pickup current is less than 1. So if it's less than 1, we are looking at a point somewhere here. So the relay is not activated. Yeah, because it's less than the threshold. But if the current is 8 amps, if the measured pickup current is 8 amps, the set value is 5. 8 on 5 is 0.33, right? So 0.33 is somewhere here, and the dial setting is 1, right? So we are looking at this curve. That's the curve we are looking at. So we need to look up here and then look up there. So it's about, relay operating time is 6 seconds, right? You can read it off the graph. If it's 15 amps, 15 amps is 2.5 times the set value. So here we are looking at 2.5, which is that. Dial setting is 1. So I go here and I go here. So it's about what, 1.2 seconds or something? Yeah, 1.2 seconds. The relay will activate in 1.2 seconds. Yeah.
What is the current tap setting in the pickup current?
Sorry?
What is the current tap setting in the pickup current? What does it mean?
Current tap setting is which curve to look at, whether we're looking at that or that or that.
Isn't the time dial setting?
Yeah, that's the time dial setting. So where is it?
So it's time dial setting of 1.
Yeah, time dial setting of 1. So that means time dial setting of 1 means we are looking at that curve. We are looking at that curve. Right?
What is the current tap setting?
Where does it say current tap? Current tap setting of 6. Yeah, current tap setting of 6 means we are looking at the multiple. It tells you the multiple to look at. This value here, current tap setting. Current tap setting tells you the multiple that you need to look here. So if the pickup current is 6, then the multiple is 1. If it's 12, pickup current is 12, 12 divided by 6 is 2, then we are looking at that number.
And the pickup current, is it after the transformer?
Yeah. Pickup current is like, after the transformer, it's how much little current that you're going to pick up from the sensor. Yeah, which is this value here. Right? In a network system, there are a number of different sources of power. Power flows are bidirectional. Now we are talking not a radial system, a mesh system. So power flows are bidirectional. Network systems offer greater reliability since the failure of a single device does not result in loss of load, because a load can be connected in many different ways. For example, we'll look at it later, but load can be supplied in many different sources, because if I got something like this, let's say that's a bus and that's a load, right? So that's the generator, that's another generator. So generator 1, generator 2. So if there is a fault somewhere here, right, we can get rid of this line and this load L can still be supplied by generator 2. Yeah? Unlike a radial system, radial network, where when there is a fault, we have to shed a load. Yeah? In a network system, there are a number of different sources of power. Power flows are bidirectional. Network system offer greater reliability since the failure of a single device or line does not result in a loss of load. Network systems are usually used with transmission system and are sometimes used with distribution systems, particularly in urban areas. Removing network elements require the operating of circuit breakers at both end of the device. So you need to remove the entire line where there is a fault. There are several common protection schemes. Multiple overlapping schemes are usually used. So we can use directional relays with communication between the device terminals. We can use impedance, which are also called distance relays. And we can also use differential protection relays as well. So let's have a look at those. Directional relays. So maybe at this point, let's take a short break, 5-minute break, and we'll come back and we'll continue. We've gone for a very long 1 hour and 10 minutes, so maybe we can do a 5-minute break. Yeah.
Does it cover content before the test as well?
Yeah, everything.
All of it?
Everything. Yeah, everything. All right, I think we can start again. So removing network elements require opening of circuit breakers at both ends of the device because the network is a mesh one. If there is a fault, you remove the entire line, take out the entire line by operating circuit breakers on both ends of the line. There are several common protection schemes. Multiple overlapping schemes are used. So we can use directional relays, impedance or distance relays, or differential protection schemes. So let's take a look at those. Directional relays are designed to operate for faults currents only in one direction. So voltage and current measurements are used to determine the flow direction. So we measure the voltage, measure the current, and then from that you can actually determine the direction. So directional relays operate like if the current flows in the correct direction, and also if the current exceeds a certain amount. So you can see there is an element here which will operate, which will determine the direction, and there is an element that deals with the overcurrent. So in order for this to occur, both direction has to be right and it has to exceed the overcurrent limit. So consider the directional relay D in the figure, right, which is the D here, the letter D in the figure, which is required to operate only for faults in the right of the current transformer. So the current needs to flow to the right of the current transformer. So here is the current transformer, it needs to flow to the right. Since the line impedance is mostly reactive, a fault at P1, which is here, fault at P1, to the right of the current transformer will have a fault current I from bus 1, this is bus 1, to bus 2 that lags bus voltage V1. So if you take the bus voltage V1, and if the current is flowing in the direction of 1 to 2, and because the line is actually inductive, the current will be lagging the voltage. So that voltage and current measurement can tell you the direction of current flow. Whereas if there is a fault at P2, the current direction will be reversed, and in this situation the current will be leading by 90 degrees instead of lagging by 90 degrees, because it will reverse by 180 degrees, right? So we can tell the forward direction and the reverse direction by measuring the voltage and current. The contacts of the overcurrent relay and the directional relay are connected in series in the figure. So overcurrent is the magnitude of the current, direction is if it's going in the correct direction, they're connected in series so that the breaker trip coil is energized only when the current secondary transformer exceeds the overcurrent relay pickup value, and also in the forward direction. So they both have to be satisfied to activate the circuit breaker. Coordinating time delay overcurrent relays can also be difficult even for some radio systems. Directional overcurrent relays are difficult to coordinate in transmission loops with multiple sources. To overcome these problems, relays that respond to voltage and current ratio can be used. So instead of the relays that we talked about so far respond to overcurrent, just or overcurrent and direction. But there can be relays that respond to the ratio of voltage to current. Because when there is a fault, the current will increase and the voltage can drop. So if the current increases 5-fold and the voltage dropped by half, then the change is 10-fold, right? The ratio will change by 10 times because we are looking at V on I. So V on I is essentially an impedance, right? It's called impedance relay as well, and they are also called distance relays because impedance also depends on how far the fault occurs down the line, because impedance changes with distance. So impedance distance relays measure ratio of voltage to current to determine if a fault exists on a particular line. So let's say x equals 0 on the left, x equals 1 on the right, let's say, right? So the fault occurs at some distance x from the left, which is 1 on x from the right, right? So V1 fault, so voltage at bus bar 1, V1, over I12 fault is approximately x times the impedance of the entire line. So you can see why this is called a distance relay, because the point where the fault occurs, the ratio of voltage to current will change as a fraction of the impedance of the entire line, which is what is stated here. Right? So in avoid to avoid inadvertent tripping of faults on other transmission lines, impedance relays are usually have several zones. Just like in the, we had time delays for, in the radial network, we had time delays associated with different circuit breakers, so that the circuit breaker closer to the fault will trip first and the others will provide backup protection. So similarly, you can have a similar setup for mesh networks by identifying zones. So zone 1 would be 80% of the line, line connecting 1 and 2, for instance. So if a fault occurs in zone 1, circuit breaker B12 will trip immediately. So this circuit breaker will trip immediately if it occurs in zone 1. So zone 1 would be 80% of the line from 1 to 2. So we can also define zone 2, and these other circuit breakers, right, will trip after a certain time. And zone 2 can cover, maybe zone 1 will cover 80% of the line, 1, 2. Zone 2 will cover maybe 120% of the line because it extends beyond the line. So zone 2 circuit breakers will operate after some time to provide backup protection. So if there something like that. And zone 3 again after a different time. So by defining zones, you can coordinate the operation of circuit breakers to provide the protection that is required. Right? So yeah, that's all I think I want to say for protection. Right? You can read a bit more on this because this is a protection is a big area in itself. So I think you can. It's about coordinating the operation of the circuit breakers by associating different time delays, and in a mesh network by identifying zones and then programming the circuit breakers accordingly. And for radial networks, of course, you want to trip the circuit breakers close to the fault first, so the upstream circuit breakers will have a longer time delay because when you trip those, upstream meaning closer to the source, so you tend to lose the entire network. So you want to trip the ones further down the line first. Yeah. So then that brings us to the next chapter, the final chapter. Sorry? Yeah? That brings us to the final chapter. It's a long chapter. On economic dispatch, transient stability, and power systems control. Right? So it's a long chapter. So I intend to cover economic dispatch today, and then after that we have 2 more lectures to go. So economic dispatch problem. What is the economic dispatch problem? Because we have we have loads, we have generators. A number of generators will be supplying the load, right? So generators not only need to supply the load, but also needs to generate the losses as well, because losses is consumed energy. So when there is a particular load demand and some losses, these generators, we need to dispatch the generators to meet the demand, and not all generating units will have the same cost of producing electricity. Some will cost less, some will cost more, right? For instance, the generators that cost the cheapest can be used as our base load. So base load are like generators that we don't stop, they will be working continuously. So examples of base load can be coal power plants, where it's used to be cheap to produce electricity because coal can be cheap. Then nuclear power plants, even though the setup cost is high, the fuels is cheaper. So it can be used as a base power plant. Then there are other generators that you need to dispatch. They can cost different amounts. There can be gas generators, there can be diesel generators, right? It will be more costly. So economic dispatch is given a particular load demand, which generators are we going to allocate to supply that load is the economic dispatch problem, right? So if we have 5 generators, you will be, let's say generator 1 and generator 2 are going cheaper, it will be used for base load. Generator 3, 4, 5, we say, okay, you this much from generator 3, this much from generator 4, and this much from generator 5, because that will provide us the least cost to provide that load. So, okay. So we can then say the cost of generating. So there are summation, there are M items, so there are M generators, right? So each generator will have a separate cost, and the cost will be a function of how much energy it produces. So it's a function of PGI. PG is a generator, I is the ith generator. So PGI is the power generator I produces. So CI, cost for generator I, CI is the cost for generator I, depends on how much it generates, PGI. And the total cost is sum of all the cost for all the M generators. The objective is to minimize that, the cost. And we have a constraint. What is the constraint? The power produced by all the generators is the second summation, I equals 1 to M PGI, must equal the load, PD, plus the losses, right? So that's the economic, to put it mathematically, economic dispatch problem is that, to put it mathematically. But I said it in words before that. So in this section, we will assume initially we'll assume that the losses are 0, right? So we have a demand, we'll assume losses are 0, so the generation must equal the demand. So we have a function that we want to minimize, which is CT, total cost is what we want to minimize, and we have a constraint. Constraint is the generation must equal the load. So that's a constraint, right? That's a constraint. So let's look at it mathematically how we do an unconstrained optimization. So let's say f is a function of x1 and x2. So unconstrained optimization requires partial derivative of f. Let's say f is the function we want to minimize. Partial derivative of f with respect to x1 must be 0. Partial derivative of f with respect to x2 must be 0. In other words, that's what we call the gradient of f, right? So partial derivatives with respect to all the variables must be 0, which is the gradient of f must be 0. Grad f must be 0, right? So that's the unconstrained optimization. So when we have a constraint, right, we can still, like, we have the function f we want to minimize, or in our case function CT, total cost of producing electricity. Then we have a constraint. So when we have a constraint optimization, we have to satisfy a constraint. A constraint optimization, we involve Lagrange multiplier. Yeah, Lagrange multiplier method. So the Lagrange multiplier method is like this. So how do you formulate this problem? Fx equal to 0 is what we're trying to, we want to minimize. Not fx equal to 0. We want to minimize fx, not fx equal to 0. We have a particular cost we want to minimize. This is the cost function, not fx equals 0, fx, right? We want to minimize fx, we want to minimize the cost is not equal to 0. We want to minimize f subject to gx equal to 0. Gx equals 0 is the constraint, right? We want this, so in this situation, what is f? F is the cost of electricity. What is Gx equal to 0 is the generation plus the load must equal 0. Right? Gx equal to 0. So in this situation, we defined a Lagrangian function. We define a Lagrangian function by saying Lx lambda, right? So we introduce another variable, x is the variable that is in function f. We introduce an additional variable lambda, and we say Lx lambda, which we define Lx lambda, and Lx lambda is fx plus lambda transpose gx. So lambda is a vector, because if you have, let's say g is a vector, g1, g2, g3. Let's say we have 3 functions. So then lambda is, we have lambda 1, lambda 2, lambda 3, right? So it's a vector. Lambda transpose gx, that's a Lagrangian function. So then the minimization is the grad of L must be 0, because L is now a function of x and also lambda. So grad of L with respect to x must be 0, grad of L with respect to lambda must be 0. In other words, grad of L must be 0. Right? With respect to all its variables must be 0. So in our economic dispatch conditions, we only have one inequality containing minimization. So because, applying the Lagrange multiplier method, so we only going to have one lambda, not several lambdas. So we have this thing. Lagrange function is the cost function, right? Cost of generating electricity plus lambda, the generation minus the demand minus generation must be 0. So that's the gx, right? Lambda times gx must is a Lagrange function. So now we need to differentiate L with respect to the variables, which is PGs, the amount that each generator is going to generate, PG1, PG2, etc. must be 0, and the partial derivative of L with respect to lambda, Lagrange multiplier must be 0. So we have these expressions. So if we differentiate with respect to PG1, right? So we just have this minus lambda, because you differentiate with respect to PG1, right? So you just get this lambda here. So you basically have these two equations. So what are these two equations telling us? These equations are basically telling us, so you need to know what the equations are telling us. This here is telling the incremental cost of generation for generator I, PGI, cost of PGI with respect to PGI, is the incremental cost of power generation in generation I. Because what is DCI, what is in the numerator? What is in the numerator is the incremental cost. Right? Incremental cost of generating a unit of power. Delta GI in the denominator, DGI, a unit of power, right? Because CI is the cost, isn't it? DCI, delta CI is a change in cost, right? Over change in power. Change in cost over change in power, right? So, so equation 1 is telling incremental cost of generating power for all, a unit of power for all the generators must equal. And must equal the value lambda, and that is the value lambda. Incremental cost of generating power for all, when it's optimized, incremental cost of generating power, a unit of power, for all the generators must be the same, and that is what you call lambda. And the second equation is simply telling the sum of power generated must equal the demand. Okay, sum of power generated is equal to demand. So let's see how to apply that in an example. So we have the cost 1 for generator 1. Cost 1 for generator 1 depends on how much power it generates, because you can see C1 is a function of P1. So if P1, if it's generating 2 watts, 2 megawatts, that will be a particular cost. If it's P1 is 5 megawatts, then C1 is a different cost. Yeah? Dollars per hour. So if the power is higher, the cost is higher. C2 is the same, depends on the power it generates, where P1 and P2 are in megawatts. Determine the power output of each unit, the incremental operating cost, right? And the total operating cost CT that minimizes CT as the total load demand PD. PT varies from 500 to 1500. Generating units, inequality constraints and transmission loss are neglected, right? So when you want to optimize it, what we do, we need to calculate the derivative of C1 with respect to the power P1, with respect to P1. So we need to look at DC1, DP1, right? We need to look at DC2, DP2, right? When it's optimized, those two need to be the same, incremental costs, and that's the value lambda, right? And power generated must equal the demand. That's what the equations are telling us. So DC1, DP1 is given by that expression. We can differentiate. DC2, DP2 can be found. We can differentiate to find that. So the lambda is when those two are equal, is the lambda value. When it's optimized, those two derivatives must equal each other, right? They are the incremental costs. So we also have P1 plus P2 must equal the demand, whatever the demand is, because what the two generators generate must equal the demand. So we have two equations with two unknowns. Right? So we have two equations and two unknowns, right? Two equations, two linear equations in this situation, two unknowns. So we can solve for P1, P2, yeah? Because if you know PD, right? The two equations are linear, so we can solve them, right? So, so we can solve for P1 and P2 if you know PD. Yeah, PD can change from what 500 to 1500. So you have different answers for P1 and P2, right? But the incremental costs are going to be the same. Yeah, so when it's 500, we have, when the demand is 500, we have P1 will be producing 206 megawatts, P2 294, and the incremental cost is $13.29 per megawatt. Incremental cost per a unit of power, per megawatt in this situation. So we need to, like, when it's optimized, incremental cost per unit of power for all the generators will be the same. Okay? So both will have the same value, which is the lambda. And when PD is 1500, the generator 1 will be providing 735 megawatts and P2 will be 765 megawatts. And the incremental cost here has increased now, 21.67 per megawatt. When you generate more power, it will cost more. For a unit of power, it will cost more. Same unit, it will cost more. Because power is not energy for the same unit of per megawatt cost is more. Right. So that's simple, that you can do, right? So if the transmission lines or losses are all ignored, doing the economic dispatch, telling which generator is producing how much is easy, because you end up with some linear equations, right? All you got to do is make sure that the incremental cost per unit of power is the same for each of the generators, and the total sum of generation must equal the load, and you have a set of linear equations. You can solve that and then you have the answer. All right, so what do we do? What do we do if we have some other constraints that we need to satisfy, apart from generation must equal the load constraint, if there are other constraints. So generators generally have limits on minimum and maximum amount of power they can produce. So a generator can have a P min and a P max. So if a generator has P min, what does that mean? It means it has to be operating all the time, and there is a minimum, it can't go below that minimum. Yeah. And if it has a P max, it means that even if the load is more, it can't generate more than that. More than that maximum. Yeah. So the load will have to be matched so that supply and demand is the same. Otherwise, we can have a blackout. Right. Oftentimes, the minimum limit is not zero. This represents a limit on the generator's operation with the desired fuel type. So fuel type will determine that. Because some fuel types like coal, you don't want to stop that. It's costly to bring it back again. Bring the power system online is costly if you stop it. Because of varying system economics, usually many generators in a system operate at their maximum megawatt level, at the rated level, at the maximums. Right? When inequality constraints are included, we modify the economic dispatch solution as follows. If one or more units reach the limit value, then the units are held at their maximum, at their limit value. In other words, if a particular generator reaches its maximum, we just hold it there. We don't try to increase more than that. If a particular generator reaches its minimum, we don't drop it any further. We just We just leave it at the minimum, right? That's what it says. The incremental operating cost of the area equals the common lambda for all the units that are not at their limits, right? So, the ones that have reached the limit no longer participate in the economic dispatch equation because they have reached the limit, and we can adjust it. We can't make it go higher if it reaches the upper. If it's lower, it's only the other generators that will participate in the economic dispatch, not the ones that have reached the limit. So here is an example. An area of an interconnected power system has two fossil fuel units operating on economic dispatch. The variable operating cost for the units are given like this. C1 for generator 1, that's the cost in terms of as a function of power it produces. For generator 2, cost is C2 as a function of power it produces. So P1 has a limit operating range 100 to 600. P2 has an operating range from 400 to 1000. When P1 and P2 are in megawatts, determine the power output of each unit, the incremental operating cost, and the total operating cost CT that minimizes CT as the total load demand PT varies from 500 to 1500 megawatts. So load varies from 500 to 1500 megawatts, but we have these additional constraints to deal with. Transmission losses are again neglected, right? So at light loads, unit 2 operates at its lower limit of 400. What happened there? No one's there anyway. Right. Yeah. Okay. So at light loads, right, unit 2, so if the total demand is smaller at light loads, right, so this generator 2 needs to provide 400, right? Generator 1 needs to provide at least 100, right? So at light loads, so if it's 500, if the load is, let's say, 500, then generator 2 must give all 400, right? And generator 1 must give all 100, because you can't go lower than that, right? So at light loads, generator 2, unit 2 operates at its lower limit of 400, where its incremental operating costs, right, is $15.2 per megawatt hour, 15.2, right? So any increase in that, we will bring in so additional loads from, so we will have unit 1 operating, everything else, for every other requirement more than 400, right, we will bring in unit 1 until its operating incremental costs reaches 15.2. So incremental cost of generator 1 is 15.2 when it produces power of 325 megawatts, right? So for PDs less than 725, P1 is less than 325 megawatts, the incremental operating cost of the area is determined by unit 1 alone. Right? Okay, let's think about, because this is important to think about it, to grasp it, right? Unit 2 is providing 400 megawatts. Incremental cost of that is 15.2 megawatts, dollars per megawatt. Now, incremental cost of generator 1 is 15.2 only when it's providing 325 megawatts. So if it's producing less than that, the incremental cost of generator 1 is less than that, isn't it? Less than 15.2. Yeah? So you keep using it until that point. Until that point, because it's going to be less. Yeah? So for PD less than 725 megawatts, we keep using P1 because it's cheaper to use, and incremental cost is only determined by P1, right? Only determined by P1 because P2 is just sitting at 400. Yeah. Operating cost is determined by P1 alone. Yeah. Because incremental cost of, because we can't go lower than 400 for generator 2. So the incremental cost for P1 equals that figure of 15.2, which is the incremental cost for generator 2, only when it's providing 325. Below that, it's lower. So we don't use generator 2 until that point. Yeah, until that point. So that's at lighter loads, right? That's at lighter loads. So lighter loads are loads which are bigger than 500, yeah, because loads can't be lower than 500. Bigger has to be bigger than 500. Yeah, bigger than, because we have two minimums, 100 and 400. Yeah, bigger than. So from 500 to 700 and till 725. For less than 725, we use generator 2 and generator 1, and incremental cost is purely determined by generator 1 for lighter loads. For heavy loads, unit 1 operates at its maximum limit of 600, right? For heavy loads, because it's 600, and the incremental cost for that will be $19.6, right? So additional loads come from unit 2 until its incremental cost is 19.6. Right? So incremental cost is 19.6 when P2 is 644 megawatts. So for PD greater than 12,044 is just P1, which is 600, right, plus the 644. For anything greater than 600, P2 is where P2 is greater than 644, the incremental cost of the area determined by unit 2 is unit 2 alone. So if PD is greater than 12,044, then P2 will determine the incremental cost because P1 has already reached the limit. Right? So that's an example that I think you can think a little bit about that. It's about when one reaches the maximum, or when one reaches its limit, it no longer takes part in it no longer determines the incremental cost of producing electricity. Yeah, it just requires just thinking a little bit there, and these numbers just show the cost of producing electricity going from 500 to 1,500. All right. So I think it's what we can do. We have one little section left to cover. I think what we can cover that in the next lecture. We can leave it here for today. Yeah.
Yeah, see.